Very good morning to the participants, and then thank you for the PKIM unit and then for arranging this knowledge transfer program. Of course, this is my personal research interest that I'm working on for the past 22 years. But okay, let me just start with what is 160 degrees centigrade, 660. So material A 1270, material B 660. If I combine these two together, I will get a new material. I call it as a NiAl or nickel aluminide. Very simple, right? So if you're looking into that a mathematical point of view, what we are expecting in terms of the number, one is 1270, another one is 660. I combine together now. The new material NiAl will have the melting temperature of around 900. Simple mathematics, right? 1270 plus 660 divide by 2. So close to 2000 divided by 2. The new material may have the temperature of only around 1000. This is simple mathematics. But surprisingly, the new material has the melting temperature of 1520 degrees centigrade. So that's what this is called intermetallics. So intermetallics, the compounds which has the property higher than the better one. Here, for example, nickel is the highest melting temperature material, 1270. Aluminium is only 660. So what I'm expecting around 1000, but the new material has the melting temperature higher than the highest. That means nickel is harder. For example, aluminium is lighter in a very simple way. But when the nickel aluminium, how it may be expecting, one is hard, one is light, it may be intermediate, right? This is not as light as aluminium. This is not as hard as nickel. This is what we are expecting, which we call alloy. But in my case or in our case, this intermetallic make the material stronger than nickel. Okay, so stronger than nickel, that means there is something intermetallic compounds which play a very specific role. Okay, coming back to our story now. So people don't want to use gold anymore because it is too expensive. Because the gold price is the one increasing every day. Never it come down. Oil price come down, increasing, fluctuating. Dollar, so money value, ringgit value goes up and goes 5. In the last 60 or 70 years, the only value which will never go down is gold, right? It may be a little bit saturated for a while, but again, it will only going up, never come down. Okay. So that is the reason they have to remove the gold aluminate with other material. Then they introduce copper aluminate. Okay. So here I'm just showing the structure. So aluminium is the common one. Gold structure is like that. This is a simple structure, how they atomically arranged. And by the time they used, become very complex structure. This is how they used previously. And later they increasing, because for example, they keep gold as one portion. They can increase the aluminium. For example, here, one portion of the gold, two portion of the aluminium. Then what they did, increasing aluminium from 50-50. Then they increase aluminium more than that. So by going this way, the structure also changes. And that's why what they did now and in the current semiconducting industry, we are no longer using the gold anymore, and we replace gold with copper, and we are using copper aluminide. Fine. But if you change from one system to another system, always there will be not only the positive, there will be some issues, right? So now the issue here with the copper aluminide is beyond certain temperature, the system breaks. So when you're manufacturing the product, it's okay. But after certain time, then it simply breaks. That's why the real smartphone, like iPhone, maybe around 4,000 ringgit. The similar function phone with the Chinese made, you can even get for 400 ringgits. But it looks same. All the functions are there. Sometimes even they give more capacity or storage into this phone. It's 10 times cheaper than the phone. But what happens? If you use something like so sophisticated, it comes very good. But even if you drop, or even if you excessively use, or even if you overcharged, are less charged. They say normally the optimum condition. So as long as you use in the optimum condition, it can come very well, no problem. But if you go beyond or either higher or lower from the optimum conditions, this phone even it can able to burst. So that's why very seldom we see iPhone is exposed, right? But the normal phones, so very often we can say when you speak along with the connection by the charger, then it is exposed. So many things we can see are exploded. So these are all due to the material that they are using, not up to the high standard. Okay, so this is about the material point of view. So then the next one we call wire bonding. So you can ask, so what is this? Wire bonding is something new word. Very simple, it is a soldering. So normal soldering, those who are very familiar with soldering, soldering is what? Take the two wire and then connect it together. Okay, so connect it together. If in a normal one, if it is a thread, we can just knot it, tie it up. In the examination question paper, we give them the thread and the students will tie up. This is one way. If it is an electrical wire, what we normally do, we use some glue and then melt the glue, connect these two wires, which may be connected together, is called soldering. But when we are going into the digital devices, the area is very small, correct? So the circuit more narrow at the atomic level or even at the minimum micro level. So if you have at the micro level and then we want to do the soldering, it's not easy because the soldering bump, normally we call the soldering paste, which itself of the size of millimeter. Okay, so 1 millimeter is 1 by 1000 of a micrometer, right? So when it is too small, then naturally we cannot use the normal soldering method. Then of course we have to use a specific method which is called wire bonding. Very simple. But because we are going into the nano level or atomic scale, this technique become very advanced technique or very sophisticated technique. Automatically it's very expensive. So normal soldering, what you need a soldering rod and you need a paste and you can do by yourself. Maybe for 50 ringgits you can able to do soldering. But for this wire bonding, the instrument alone will be about 2.8 million US dollar. One soldering machine, a wire bonding, because of the small size. So very simple, like Intel, Infineon, Texas Instruments, all those semiconducting industries, they are using this technique is called wire bonding. Of course, it has some methodology, not just directly soldering it. I will explain little bit about what it is. So this is what we are going to now look at. After looking at the material, how this material can be used by the technique is called wire bonding. In a very simpler manner, if you don't have an electronic background, what is wire bonding is nothing but soldering. That's it. To connecting to wire. But wire bonding is a joining technique to produce discrete electrical contact. The word discrete normally we can say very small elements. Wire bonding technique, there are few. So we have a thermocompression method, thermosonic method, ultrasonic method. So thermocompression is increase the temperature. When we increase the temperature, what normally happens? The material gets shrinking, smaller. And when this becomes smaller and then expanding it, and that will help the material to stick it. So this is what we call thermocompression. So normally this thermocompression bond is the result of bringing two metal surfaces together in intimate contact during controlled time, temperature and pressure cycle. So normally this intimate, even we normally talk about between the husband and wife, right? Intimacy. So too close, nano gap, we say, right? So something similar. So there is a gap, but it's very, very small. So similarly, the intimate contact means the two wires are so narrow, but it is not touching each other. So this kind of technique which normally use called thermocompression. The another one we normally call is ultrasonic bonding, or we normally call wedge bonding. I will give a small video clip later. I will show you how it looks like. It's a low temperature process because not every material can withstand at high temperature. There are materials which are very sensitive to temperature. If you go 100 degrees C, the material already started to melt because we are talking about a nano wire, right? Very, very thin wire. So even when the temperature is slowly increasing from room temperature to 60, 80, 100, etc., the material started to behave. So what we normally do, we use a low temperature process. Here, low temperature doesn't means negative temperature, not chilled temperature. Huh? So meaning to say low temperature here between 20 to 30 degrees C. We just go very mild heating. So when there is a mild heating, so there may be some changes will take place, but commercially we don't use it much. Huh? So only for the experimental purpose. Because companies like Infineon, they want to produce one day 300,000 components or chips in a simpler way. Huh? So, but by using the ultrasonic bonding, they can create only 4. So they won't do that. Okay. So commercially, we will be still using the thermocompression or thermosonic, because what they do, thermocompression is mainly temperature which is combined or compressed, put together. Ultrasonic is normally we send the rays but without touching it. So the new technique we use ultra little bit over here and then thermal over here, then we call it as a thermosonic technique. So we still use temperature, but the temperature will be using with non-contact. Okay, so this is the method. Normally, wire bonding is one of the important assembly technologies used to make the electronic interconnection. So what is thermosonic is ultrasonic plus thermal energies. So this is the picture, but I have a kind of animation. So this is how. So all the wires are connected and soldered at one end, and the other end just be connected. And this is, you can see here, the right hand side picture. This looks like very big, but this is the size of 0.1 micron. 0.1 micron is actually 100 nanometer. Okay. So this is as small as this. It's very difficult to do the normal soldering. So what they do, we use the wire. The wire must be thinner than the circuit, correct? Then only we can able to do that. So if I say this is 0.1 micron or 100 nanometer, the wire must be 10 nanometer, for example, or maybe 2 nanometer. So the more and more thinner we go, what is the problem? It will fail very often, high chances. So it has to be like more reliable. That is the advantage of gold wire. So the gold wire, even though we go as thin as possible, it will not break easily. But the other materials, the more thinner we go, it will break. So just for the comparison, previously I said there was 4 gram of gold was used in the electronic network to connect about 7.2 kilometers, right? But if you go to the copper, we have to use at least 4 to 5 times, not just 4 gram of copper we have to use, minimum 16 to 20 gram of copper. But when you consider the overall laptop size, it may be 1.2 kg or even 1.5 kg, this additional 15 gram, not really a big matter, correct? But the price will come down. Let's say if 1 gram of gold is 200 ringgit, 4 gram of gold is 800 ringgit. Now this 20 gram of high quality copper will come only 40 ringgits. So in terms of the soldering expenses, the wire bonding process, the price will come down from 800 to 40. Okay. So it's only 1 by 20 of the original cost. So people, of course, automatically the price of the laptop also can come down. So these are all one of the method. So you can see how small they normally used to be and then how closely they used to be. So this is what we can see, the nano type of wires. Okay. And I can just show you, this is how the soldering normally takes place. Again, this is at the nano level. Okay. So this is what we call a thin wire. What this wire? So this wire, this small wire, now we magnify up to this thing. So then we can imagine how good it is. Okay, so these are all method, but I have this animation which will tell us this is nothing much. I will go faster. What is happening? The lead is the one way of connection. This is the bond pad, and this is where the free air ball. That means the soldering paste will be coming down. then this will be connected. So I just move fastly, then we can feel that. So it's again getting the force going up and then moving to the other side and then connected with respect to the temperature. So because if you see previously little bit, so once it comes over there, no physical contact. You can see until now, no physical contact. But what makes them to be at contact here? Temperature. So now we can see that there is a temperature increased. When the small temperature increase, the wire will get expanded. I'm not saying melted, expanding a bit and then stick together with the things. So this is how normally they are doing. So after that, it goes up. So the wire is bonded now. So now if I go back, this is what we can call about the wire bonding technique. So what is there? Previously they used gold wire bonding, and because of the price which is keep on increasing, now we are going with the copper wire bonding. And of course, by moving from gold to copper, there are some issues. So I actually received a crust grant with the collaboration of Infineon in 2013 until 2018. A 5 years grant. I got about 800K from the crust, collaborative research in science and technology. And then we have find out few results, and then 2 students were graduated for their PhD, and it is still going on. Okay, so the wire bonding technique. So far previously I explained only theoretically. We just see some video clip how the wire bonding can take place. Can you able to hear the sound, and also we can see the video, right?
Yes, Prof.
Yes.
Thank you.
Okay, thank you very much. Okay, I play again. This was previous one, how the gold wire bonding. Okay, so that was about the previously what we used as a gold wire bonding. So now we no longer using it, and then we are now using the copper wire ball bonding. And we can also see that how this will looks like. Okay. So of course, when we introduce any new technology, there will be some issues. So as I told you now, the recent one, the copper has some voids formation at the bonding interface. Void is normally bubble. So when we talk about void, what is the scientific word? The general one, we can say a bubble. So there is a extra space created between during the soldering, which is making the system to be the premature failure. And for this only, we are working on it. So my PhD students are working on that. So until now, what I have mentioned is only a general one. So now only I'm going into what actually our part, our research part, because I know that not the participants are having the previous knowledge. So I spend more time on the introductory part. Of course, since we are dealing with the nano level, of course, we have to use a transmission electron microscope or TEM as our major method to study this problem, which is just now we have mentioned that the voids formation at the bonding interface, which makes the system to be premature failure. So that means when they have come up with any digital circuit, then we can see there is a failure over there, especially at this particular temperature. That means in the quality test, it is failed. So that's where now we are working on it, how we can play. Of course, we found some solutions for it, though it may not be something, change from material A to material B. We have extending some of the working hours, etc. And these are the some of the results. But there are few things we need to understand. So what's so special about aluminum alloys? Because you will be talking about, so you previously you said aluminum alloy, copper alloy, gold alloy. So whatever the alloy you're talking about, aluminum is always second part of it. Aluminum never changes. Previously it was gold. Now we are using copper, and sometimes we use nickel, again nickel aluminum, gold aluminium, copper aluminium, titanium aluminium, etc. Because aluminium has some specific quantities. Most of us, sometimes we don't understand the aluminium. The pure aluminium is 5 times expensive than iron. Okay. But we think aluminium normally is much cheaper, right? Or maybe more economical compared to other material. But in reality, the pure aluminium is more expensive than iron. How do I know? all the high-end cars, right? Like Audi, Volvo, BMW, Benz, they all use the body chassis, car chassis as aluminium. So aluminium is lightweight, but it has more ductile in nature. So that's why maybe because we have some time, I can tell a small story. So it's a story. There was a businessman who gave a party. So everyone invited because nice food, so everybody joins. We don't care, right? Why they are giving a party. As long as the food is nice, we go. Because it's not just we go, they are inviting. So let's say I'm inviting you all, hey, join for today's party. So maybe, okay, because Prof is inviting, I'm going for his party. And then he said, these are all the menu. So after doing everything, in between the meal time, the businessman said, you know what happened today? I lost my car. Huh? What, this fellow is crazy or what? What kind of car you lost? I lost my new Mercedes-Benz car. Total damage. Okay, fine. So this is what he said. And everybody now, while eating, they all got panic. This fellow is crazy or what? He said he lost his new Mercedes-Benz this morning and he's giving a party this evening. Then he said, I was the driver. So that means even though the car is total damage, nothing happened to me because he's telling I'm a businessman. If I lose this car, in my lifetime, I can even buy 100 Mercedes-Benz. No problem. I can earn because I have the capability to do that. But if I lose my small finger, I cannot get back. Or even if I get an artificial one, it will not give me the original worth. Okay. So even though my car is total damage today or I lost everything, nothing happened to me. So it saved my life. So I'm giving you this party. Okay. This is a story, but it is also a real incident. What we can see here, that's why whenever the automotive industry, when the normal cars, for example, the budget cars that we are referring, we use the iron body, ferrum. But what is the structure of the iron is normally needle structure. So needle means it's like a needle. So during the collision, when there is an accident, this iron particles will come as a needle and it will make more damage. Whereas materials such as aluminium, during the accident, it's become an X shape. Okay. So you go and hit very fast, and if you wear the seat belt and then all the airbags comes out, even though the car is externally total damage, internally nothing will happen because it will change the shape like a egg, and within the egg you are there, you are very safe. Of course, this is aluminium. So more than aluminium, we have titanium. So titanium, normally they use cars such as Ferrari, Lamborghini. So that's why the car prices is increasing. Because even in Proton, we are using Mitsubishi engine, right? So Mitsubishi engine means not Mitsubishi name, the same engine that what the Mitsubishi car is using. In Malaysia, we are using for Proton. So that means the engine quality is still same. Then where the price difference? It's mainly because of the interior and then the chassis, etc. Because the normal budget cars for the chassis, we may be using iron-based or ferrum-based, whereas the high-end cars, they are using either aluminium body or it could be titanium, something like that. So these are all more expensive. Okay, so coming back to aluminium, what is so special about aluminium? So some little bit properties. So conventional alloys have lower strength weight ratio than titanium, but more advanced alloys approach. Of course, titanium is one of the very good material, lightweight, more stronger, that everybody knows. But we cannot use titanium everywhere, right? Titanium can be used in jet engine or jet plane or cars such as Lamborghini and Ferrari because they are millions of price. So equal to the titanium, aluminium alloys is also have the similar property. For example, specific gravity of the aluminium is 2.8, which we can compare that, which is equivalent to 62% of that of titanium. So meaning to say, in terms of the price, it's a commercial value. It may not be accurate. Titanium 1 kilogram maybe 1,000 ringgit, for example. Aluminium 1 kilogram maybe only 50 ringgit. But in terms of the quality, if I purchase maybe 2 kilogram of aluminium, which is equivalent to 1 kilogram of titanium. But 2 kilogram of aluminum is only 100 ringgit. 1 gram of titanium, 1 kilogram of titanium is 1000 ringgit, right? But still I can able to get similar property. So this is how we can normally compare. Huh? So the specific gravity of the iron ore, if you compare it, may be only 10 to 15% of that titanium. So that's why for the normal situation, we may not use it. Okay. But the source specialty is this is lower cost than titanium, of course. And then the maximum temperature for advanced alloys, it can go up to 350 degrees centigrade. So when there is an accident, for example, in any automotive, the temperature is expected to go easily 300 degrees centigrade. Huh? So 300, normal temperature is 25-30. And when we feel very hot, it is 40 degrees centigrade. The water boiling temperature is about 98 degree, 98.4 degrees centigrade, whereby the water is boiling. Okay. But this assume 300 degrees C is already very high. It is the normal accidental temperature. But what we can see, this aluminum can go up to 350 degrees centigrade. The property will not change. Only more than 350, the property will start to change. Now you can ask a question. Just now you said aluminum is only 350, it can withstand. Iron is more stronger than this, correct? So then why you say that iron is not good? Because the moment iron, the structure will change. It will become a needle structure. Needle is, sharp edge. So when there is an accident or when there is a small mechanical shock, the iron pieces will not become a X kind of shape, it coming like a needle shape, which makes the passenger or maybe the people driving the car makes the accident to be more worst. And more so when it is become needle and during the accident, when the temperature increases, it can catch fire easily. Okay, so these are all some of the reason. Of course, the other specialty of aluminium, it has a lower weight and rotating inertia also. And this is just those who are really interested to know the material from one to another, how the crystal structure and all other properties, which makes this copper aluminium can be the suitable material to replace the gold material. And these are all some of our recent findings. And of course, we publish in the high-end Q1 journals like material chemistry and physics. And these are all some of our results. I think I can just show and no need to explain much. So how it can be, because it will take much more time. In case if any of you are very familiar with these kind of things, maybe I can explain a bit. For example, this is what we can go into the nano structure. Nano is about, you can see, about 46 nanometer. So the thickness of the intermetallic compound is estimated at 46. So that means this whole the whole rectangular is about only 46 nanometer. So that means we can imagine that how small we are looking at. We are actually looking at the atomic scale things. Okay, so these are all the publications we have performed using that. And just to summarize, so previously people were using intermetallic system with gold aluminide, and slowly we are changing with the copper aluminide, but it has some problems with when the temperature goes up to 175 degrees C, there may be something which we call void formation, or there is some bubbles formation, which makes the continuity issue. So then we change some kind of material adjustment, meaning the ratio between copper and aluminium, and also we increase the ball edge samples from 0 hour to 500 hours to 1000 hours, then we can see that it may be better. Because what we can observe here, in the case of IMC growth, which is in the smaller one, 0 hour, it's only nanometer. But when we go up to 500 and then 1000 degrees centigrade, the IMC growth, that means the intermetallic compound growth, can go up to 1.2 micrometer. So whereby there is all the bubbles and voids can be replaced from it. Okay, so these are all some of the references. And in this occasion, I would like to thank for this presentation, which is involved the results from my PhD students who already graduated. Dr. Chua Kokiao and Sarisha is submitting her thesis next week. And of course, some of my master students and with the collaborators either at the national level, international level. Of course, not to forget the people from Infineon, which are all our collaborators. And I would like to acknowledge our COSIDA, so the research group, of course, UTEM, the research funding by the CRUST, and then SUSROM, Infineon, of course, the current faculty, what they are is FTKMP. Thanks to everyone. And of course, I'm happy to share if you have any questions or anything. I hope I finish it on time. I know at the one some areas I move faster. It's mainly due to there are limited participants, so I feel that the introductory part I give more time to explain what is IMC, why it is important, what is the difference between IMC and the other alloys and compounds. Then our research results part I just shown little bit but not discussed in detail. Thank you very much.